here on 1 through 4, we're asked to match each slope field with the differential equation. And if the slope field is autonomous, to be autonomous, the derivative is equal to a function of just y. Then draw the phase line. We're going to look at this and look to see what it looks like. We'll find the critical points, and we'll label each point as stable, unstable, or semi-stable. And I'll explain this as we go through these. Now, on this first equation, the dy dx equals y minus 1 times y plus 3. Notice that our derivative is a function of y. Therefore, this first equation is autonomous. Now, a phase line is a line that tells you when your slope is positive and when your slope is negative. So the slope is the same as the derivative, and so if I take this derivative and set it equal to 0 and solve the equation, 0 equals y minus 1 times y plus 3, then we can apply the zero factor property, and solve both of these equations so that this first equation becomes y is equal to 1 and the second equation becomes y equals negative 3. These are the critical points. The critical points are where the slope is equal to 0. And so I'm going to put them on my phase line, which is just the y-axis essentially. I'll put negative 3 down here, I'll put 1 up here, and at both of these points the slope is 0. I'm also going to draw a phase portrait similar to these 4 at the bottom. On my phase portrait, I'm going to put my x and y axis in the middle, kind of in the middle, and y equals negative 3 I'll put down here, y equals 1 about here, and I know that my slope is 0 at both of these points. So I'll go across. That's at 1. Those are horizontal line segments at negative 3, right there. Now what I want to do is I want to look at what's happening above y equals 1. Let me label it here also. Y equals 1, y equals negative 3. Above y equals 1, is my slope positive? Is my graph going up? Or is my slope negative? Is it going down? Whether it goes up or whether it goes down, it's always going to be approaching this horizontal line segment. So as you get closer to the horizontal line segment, your line is going to start to level out. So we can go back to this equation, 0 equals y minus 1 times y plus 3, and select a test value. In my first region, a test value above 1. I'm going to choose a test value of 2, and when I test 2, let me test it right here. I'm going to get my derivative is equal to 2 minus 1 times 2 plus 3, and really all we're looking for is positive or negative. I'll get 1 times 5 or 5, which is positive. On your phase line, you show positive with the line going up from the critical value. Goes up here. Up, up. On the slope field, when y is equal to 2, 2 is about here, my slope is 5. 5 is pretty steep. A slope of 5 means for every 5 units you go up, you go 1 to the right. So it's a fairly steep curve. I'll put it like that. And I know that it's leveling out as it gets closer. So in between this value of 2 and y equals 1, I'm going to show that the line is leveling out. We can see that above y equals 1, if I start at any point, my line is going to go up and to the right. Okay, so let's choose a test value between 1 and -3. An excellent test value to choose would be 0. And at 0, if I substitute it into my derivative, I'm going to get 0 minus 1. I'm going to get 0 plus 3. That gives me a -1 times 3, or -3. That's negative. And so in between 1 and -3, my line will be decreasing. My slope is negative. And a slope of -3, let me do that over here. A slope of -3 says for every 3 units you go down, go 1 unit to the right. Your line's going to look something like that. And so along this line where y is equal to 0, I'm going to draw little line segments that have slopes that are approximately -3. And again, as I approach this critical value, my line is leveling out. As I approach this critical level at -3, my line levels out. If you want to, you can calculate the slope at -1 and -2, get a little bit more accurate picture, but I think this is doing pretty good. And then in the last region, we want to see what's happening below x equals -3. Is our line coming up to meet this critical value, or is it going away from the critical value? And so we'll go back here and choose a test point at maybe -4. Substituting -4 in, I'm going to get, I'll do this off to the side. I'm going to get -4 minus 1, and -4 plus 3. That gives me -5 times -1, or 5. And so my slope is positive in this last region, is going up. And that was at -4. That's a fairly steep slope. And I'll bring it so that it shows that it's leveling out here a little bit too. Okay, so what the slope field does is it shows what's happening over time. If my line starts at this point that I highlighted before, then my line is going to follow these little slope marks that I made. It's going to go up and to the right. If I start right on y equals 1, then my line is going to go horizontal. Let me change the colors so that we can look at some of these. Okay. So again, if I start at this point that I highlighted initially, then my line is going to go up and to the right. And it'll continue going in that direction forever. There it is. if I start right on one of my critical values, there it is, anywhere on the critical values, then my line may go straight across, but you have these forces right above and these forces right below that are pulling you in those directions. And so this might decide to head up at any point if it's not exactly on y equals 1, or it might decide to head down. Because at y equals 1, let me change this. Because at y equals 1, these forces are pulling the line in two different directions. This point is said to be unstable. Y equals 1 is unstable. It's also called a repeller because it repels whatever comes near it. It pushes it back in the other direction. Change that a little bit different. Okay, if I start anywhere here between 1 and -3, y equals 1 and -3, my line is going to go down and start leveling off at -3. If I start right on -3, then my graph is going to stay right on -3. Notice that from below my graph is coming up, from above my graph is coming down. So here at -3, chances are that my graph won't just be pulled by some unseen force outwards. This one, both sides are pushing towards y equals -3. And -3, this is called a stable critical value, and it's also called an attractor. It attracts from both above and below. So at -3, this is stable, or also called attractor. And notice that if you start from below, somewhere down here, your flow is going to go up and start to level out at y equals -3. So your slope field tells you, depending upon what critical value you're given, it's going to tell you what your line is going to look like. Notice that in this case, no matter where I start between 1 and -3, my function looks very similar. But if you start above y equals 1, your graph is going to increase. If you start below, it's going to go to y equals 3, and so forth. Here, because this is an autonomous ODE, it depends upon the values of y and not the values of x. So if you take any one of these slices, let me do a highlighter. If you take a slice, a vertical slice, this vertical slice that I took would look the same as this vertical slice. Or they should, if I drew it correctly. Then once we have this drawn, we can go, and we know we have critical values at 1 and critical values at -3. So that looks like graph B. Here's my critical value at 1. Here's my critical value at -3. And if we check the slopes, above 1 it's a positive slope. you can see this is kind of going up, and it's fairly steep. Remember, we have a slope of 5 real close to the critical value. In between 1 and -3, our graph should be going down, and you can see that this is going down. And then from below, the graph is coming up, and is still steep coming up. And our slope is positive below -3. So on this, B is the answer to number 1.